Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today, we are going to discuss lecture 3 in thermodynamics, new topic in thermodynamics. So, it is based on heat capacity. So, already we have done up to first law of thermodynamics. Now, let us see some more topics in thermodynamics. Yes. So, please listen carefully. So, this class we are going to discuss about heat capacity. This is also an important area in thermodynamics. So far we have done first law of thermodynamics, internal energy, etc. problems also. Now we are going to do new problems, that is heat capacity. So what is heat capacity we are going to discuss now. It is also a very important concept. So what is heat capacity? Numericals based on heat capacity, definitely they are going to give you entrance exams. So that's why this is more important. Now let us see what is heat capacity. When we heat a system, the increase in temperature of the system. When we heat a system, the increase in temperature of the system is directly proportional to the amount of heat absorbed. So Q is called amount of heat absorbed and it is proportional to absolute temperature, or Q is equal to CT, where C is called heat capacity. C is called heat capacity of the system, which depends on the size and nature of the system. So C is called. So when we heat a system, the increase in temperature of the system, the increase in temperature of the system is directly proportional to the amount of heat absorbed. So C is the heat capacity of the system. So since Q is proportional to absolute temperature, so Q is equal to C into T, where C is called heat capacity of the system. So it can be done in two ways. That is heat capacity of system at constant pressure and heat capacity of the system at constant volume. So this is called heat capacity of the system. Heat capacity at constant pressure. At constant pressure. And this heat capacity of system at constant volume. Heat capacity at constant volume. So you can take either this or this depending on the numerical. So what is heat capacity? When we heat a system, the increase in temperature of the system is directly proportional to the amount of heat absorbed. So this is called Q is proportionality, and for removing proportionality, we have to use constant, that is called heat capacity. And if C is large, more heat is required to raise the temperature of the system by a specific amount. So depending on the value of C, we can give the heat. I hope it is clear. Let us see now. If T is equal to 1, that is temperature is equal to 1, then Q is equal to C, because since Q is equal to CT, so automatically Q is equal to C. Hence, heat capacity of system is defined as, the amount of heat required to raise the temperature of a system by 1 degree C or 1 Kelvin is called as heat capacity, just like specific heat. Specific heat. So what is specific heat? The amount of heat required to raise the temperature of the system by 1 degree C or 1 Kelvin is called heat capacity, where C is equal to differentiation of Q by differentiation of T, or C is equal to Q by delta T, assuming to be constant over the given temperature range. Heat to be constant. What is to be constant? Q to be constant, that is heat over the given temperature range. So C is equal to Q by delta T. What is dq? Differentiation of Q, that is change in heat. Differentiation of temperature, that is change in temperature. What is C? C is called heat capacity. Heat capacity is an extensive property because it depends upon the temperature. So automatically it is an extensive property and a path function. So it is an extensive property and a path function. So I hope it is clear what is heat capacity. Let us see now. Molar heat capacity. It is the amount of heat required to raise the temperature of a substance by 1 degree C or 1 Kelvin. It is called molar amount of heat to raise the temperature of 1 mole of a substance. Here we have to write 1 mole of a substance here. 1 mole of a substance. because the difference between heat capacity and molar heat capacity means for molar heat capacity will take 1 mole of a substance. So the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree C or 1 Kelvin is called as molar heat capacity. Its units is joules per Kelvin per mole. Joules per Kelvin per mole, because Q is in joules and temperature is in Kelvin, and moles, N is called number of moles, that is weight by molecular weight. So Cm is equal to, that is molar heat capacity, Cm is equal to Q by N delta T, where N is called number of moles and delta T is called change in temperature, Q is called amount of heat. Molar capacity is an intensive property and a path function, very important. Molar heat capacity, because it is depending on 1 mole of a substance. So molar heat capacity is an intensive property, very, very important. Heat capacity is an extensive property, but molar heat capacity is an intensive property. For gases, molar heat capacity can be defined as at constant volume or at constant pressure, as I told you. For gases, we will define molar heat capacity at constant pressure and molar heat capacity at constant volume. So Cp and Cv. I hope it is clear. So for the gases, molar heat capacity can be defined at constant volume or at constant pressure. So this is constant pressure, this is constant volume. Molar heat capacity at constant pressure, molar heat capacity at constant volume. And this is equal to Cp is equal to Q by N delta T. This is the formula where Q is called amount of heat given to the substance, N is called number of moles, delta T is change in temperature. I hope it is clear. So all these formulas we are going to do numericals in this class now. So please note it down. Next, molar heat capacity at constant volume. It is the amount of heat required to raise the temperature of 1 mole of a substance. Again, here 1 mole is missing. So amount of substance of 1 mole of a substance. 1 mole of a substance by 1 degree C or 1 Kelvin at constant volume. This is called molar heat capacity at constant volume. Simple. It is amount of heat required to raise the temperature of 1 mole of a substance by 1 degree C. 1 mole of a gas you can test right away. Instead of writing substance, we can take gas directly. 1 mole of a gas by 1 degree C or 1 Kelvin at constant volume. So Cv is equal to du by dt, where du is called change in internal energy. This formula is very important. Du is called what? Change in enthalpy or internal energy. So du or delta U or delta E all are same. That is change in enthalpies, change in internal energy, and differentiation of internal energy. So du is equal to Cv dt or delta U is equal to Cv delta T. That is change in internal energy is equal to Cv delta T. This type of numericals are most important. So delta U is equal to Cv delta T. Similarly, delta U is equal to Cp delta T. Cp delta T, where delta T is called change in temperature, delta U is called change in internal energy or change in enthalpy, and Cp is called specific heat capacity at molar heat capacity at constant volume, constant pressure, sorry. I hope it is clear. So what is molar heat capacity at constant volume? It is the amount of heat required to raise the temperature of 1 mole of a substance by 1 mole of a gas by 1 degree C at constant volume. At constant volume is important here. Next, again, molar heat capacity at constant pressure. At constant pressure, it is the amount of heat required to raise the temperature of a 1 mole of a substance, 1 mole of a gas, 1 mole. Again, here 1 mole is mistake. So 1 mole of a substance, that is nothing but gas, by 1 degree C or 1 Kelvin at constant pressure. So same formula, delta H is equal to Cp delta T, where delta H is called enthalpy, heat of formation. For solids and liquids, the difference between Cp and Cv is negligible. Very, very important point. For solids and liquids, the difference between Cp and Cv. What is Cp? Molar heat capacity at constant pressure. What is Cv? Molar heat capacity at constant volume. And here DH is called heat of differentiation of heat. So delta H is nothing but what? Enthalpy, heat of formation. So molar heat capacity at constant pressure and at constant volume are intensive properties, because they are 1 mole of substance. They are representing only 1 mole. It is not depending on quantity. Since it is not depending on quantity, they are called as intensive properties. So Cp and Cv are called intrinsic properties. So molar heat capacity, constant pressure and at constant volume are intrinsic properties. I hope it is clear. Next, relation between Cp and Cv for an ideal gas. When heat is observed at constant volume, no work is done. When heat is observed at constant volume, no work is done. But when heat is observed at constant pressure, volume increases and work is done. Extra energy is required to do this work. So very, very important, these 2 points, very important. Please note it down. Based on this, they'll ask statement-based question. When heat is absorbed at constant volume, no work is done. Why? Because volume is constant, so temperature is constant. If temperature is constant, automatically work done is constant because work done is equal to minus P delta V. Since work done is equal to minus P delta V, since volume is constant, work done becomes zero because delta V becomes zero. Since delta V becomes zero, automatically, since at constant volume, what happens? Delta V becomes zero. So automatically work done is equal to zero. So no work is done. But when heat is absorbed at constant pressure, volume increases and work is done. Extra energy is required to do this work. Hence, Cp is always greater than Cv. Cp is always greater than Cv. And H is equal to U plus PV. This already we know from first law of thermodynamics. And H is equal to U plus PV is equal to RT for an ideal gas. So for 1 mole of an ideal gas, PV is equal to RT because PV is equal to nRT. So we can write H is equal to delta H is equal to delta U plus R delta T. This is the formula for finding delta H, delta U plus the R delta T for 1 mole of an ideal gas. For only for 1 mole of N moles of an ideal gas, N delta N RT. So that also we discuss. So next. So why work is not done at constant volume? Because at constant volume delta V becomes zero. So automatically work done becomes zero. Since already we know work done is equal to minus P into delta V. So when heat is observed at constant volume, no work is done. But when heat is observed at constant pressure, volume increases and work is done. So to find that work, you can do like this. I hope it is clear. If you do numericals, you can understand clearly. Yes, copy down whatever is given in the PPTs. Now delta H is equal to Cp delta T or delta is equal to Cv delta T. So Cp delta T is equal to, find this, the relation between Cp and Cv. Cp delta T is equal to Cv delta T plus R delta T. So Cp is equal to Cv plus R, Cp minus Cv is equal to R because taking delta T is common. So Cp minus Cv is always equal to R, where R is called, what is R? R is called universal gas constant. Universal gas constant. Its value is R is equal to 8.314 joules per Kelvin per mole. I hope it is clear. So Cp minus Cv is equal to R. This topic is there in physics also, but in chemistry the questions will be different. Specific heat capacity. This is what? Specific heat capacity. Molar heat capacity and specific heat capacity. What is the difference? Simple, only definition is same. It is the amount of heat required to raise the temperature of unit mass. Unit mass is important. 1 gram or 1 kg of a substance by 1 degree C or 1 Kelvin. That is called specific heat capacity. And specific heat capacity, just like molar heat capacity, specific heat capacity of gas is defined at constant volume and at constant pressure. And most important, specific heat capacity is also an intensive property, just like molar heat capacity. So specific heat is equal to S is equal to Q by M delta T, where M is called mass of the substance in grams. I hope it is clear. Next, relation between molar heat capacity and specific heat capacity. Molar heat capacity is equal to specific heat into molar mass, and therefore Cp minus Cv is equal to R. And molar heat capacity and molar minus is equal to R. So by this specific heat capacity at constant pressure and specific heat capacity at constant volume is equal to R by M. What is M? M is called mass of the substance, because mass into specific heat capacity of constant pressure and mass in minus mass into specific heat capacity at constant volume is equal to R. That is the difference. Because the difference between molar mass and the specific heat capacity is only unit mass. Since it is based on unit mass, because specific is nothing but molar mass. So unit mass, so that's why we are taking molar mass, molar mass. So these formulas are important. Specific heat capacity at constant pressure and specific heat capacity at constant volume. So specific, the difference between specific heat capacity at constant pressure and minus constant volume is specific heat capacity constant volume is R by M, where R is called gas constant, M is called molar mass of the substance. I hope it is clear. Very, very important this formula. Similarly, the difference between specific heat capacity, that also we have discussed. Next. So next concept in this, now we are going to discuss. So what is specific heat capacity we have done already. Now we are going to do new topic, that is calculations based upon heat absorbed by a system. So calculations based on heat absorbed by a system. Calculations of heat absorbed by a system. Heat absorbed by a system. If the temperature of m grams of substance is raised from T1 to T2, this formula is very, very important. Suppose we are taking m grams of a substance, either it is gas or liquid or solid. It is raised from temperature T1 to T2. Means if you are giving temperature, automatically that substance raised from T1 to T2, either at constant pressure or at constant volume. Then the amount of heat absorbed is given by QP is equal to M into specific heat capacity at constant pressure, T2 minus T1, or QV is equal to M into SV into T2 minus T1. So this formula is important. This is specific heat capacity at constant pressure into change in temperature, mass into specific heat capacity at constant volume into change in temperature. So either you can find the amount of heat absorbed at constant pressure and constant volume is given by the formula mass into specific heat capacity at constant pressure into T2 minus T1, and QV is equal to mass into specific heat capacity at constant volume into T2 minus T1. I hope it is clear. Next. Calculation of heat absorbed by a system. Continuation. The heat absorbed by n moles of a substance is given by n moles, because number of moles if you take into consideration, QP is equal to n into Cp. That is, Cp means what? Molar heat capacity. When you are taking moles, automatically you'll get into picture molar heat capacity. What is Cp? Cp is called, Cp is equal to molar heat capacity at constant pressure. Molar heat capacity of a substance, molar heat capacity at constant pressure. What is Sp? Specific heat capacity. Specific heat capacity of the same substance at constant pressure. Specific heat at constant pressure. That's why for Sp we are taking m, that is mass of the substance, whereas for Cp we are taking n, where n is called number of moles. N is called number of moles. So that's why Qp is equal to n into Cp into T2 minus T1. Qv is equal to n into Cv into T2 minus T1. The heat absorbed by a calorimeter is given by heat capacity of the calorimeter, that is Cp into T2 minus T1. So Q is equal to, so usually what is this calorimeter? Calorimeter is nothing but where you will find it's called as bomb calorimeter. You can find method of mixtures. We can find heat capacity of the mixture and heat absorbed. So for studying heat reactions, we use bomb calorimeter to study or observe heat reactions. Heat reactions, we use bomb calorimeter. This is called bomb calorimeter. Bomb calorimeter. Very, very important. Next. So difference between number of moles for molar heat capacity and mass for specific heat capacity. I hope it is clear. Now let us see the question. Calculate the amount of heat needed to raise the temperature of 10 grams of iron. They have given what? Mass of iron. From 25 degrees C to 500 degrees C. So temperature is T1 is equal to 25, T2 is 500. The specific heat capacity, see here, this is SV of iron is 0.45 grams joules per degree C per gram. Then what is the amount of heat needed? So we have to find, they have given specific heat capacity of iron, and it is not constant, it is constant pressure actually, because SP we can say, because pressure is not given. Also, the calculate the mass of gold. Second one, we have to find mass. Specific heat capacity of gold is given. S of gold is given. That can be heated to the same temperature difference when supplied with the same amount of heat. So whatever the heat given in the first one, same heat is given. So let us solve this numerical now. So already we know QP is equal to, so QV is equal to, QP is equal to M into SP into T2 minus T1. So what is mass of iron? That is 10 grams. First we are finding heat needed to rise. So 10 into SP, that is specific heat of iron, is given how much? It is 0.45 into T2 minus T1, 500 minus 25 degrees C. Temperature, Kelvin difference, both are same. So directly I'm taking 500 minus 25. 500 minus 25 is 475. So if you multiply this all, you'll get the value. It is equal to 2137.5 joules. 2137.5 joules. Writing neatly. So after multiplying this, you got 2137.5 joules. Now, second case. This is first case over. Second case. How to calculate? Second case, what they're asking, mass. But they are giving same amount of heat, means this much heat. So second case, 2137.5 is equal to mass of gold, which we are going to find, into specific heat of gold is given how much? 0.13. 0.13, because specific heat of gold is given 0.13, and into temperature difference is same temperature difference, that is 475. So by this we can say M is equal to 2137.5 by 0.13 into 475. So if you calculate this, you will get it as 34.61 grams. So this is the answer. So I hope it is clear. Let us check the answers. So as I told you, in the first case, 2137.5 joules. In second case, it is 34.61 grams. Here, directly why you are taking iron weight? Because they are given specific heat capacity. When they are given specific heat capacity, we have to consider only mass. When they are given molar heat capacity, that is CV, CP, or CV, then we have to consider number of moles. But they are given only specific heat capacity. So please find the difference. When they are given specific heat capacity, we have to consider only mass. So QP is, that is the amount of heat required at constant pressure, is equal to mass of the substance into specific heat capacity of the substance into temperature difference. And QP is equal to M into SP into T2 minus T1. So we got it as 10 into 0.45, because it is given zero specific heat capacity of iron is, and mass of iron is 10 grams. So it is equal to, that is temperature difference is 475, it is equal to 2137.5 joules. Now taking this heat, same amount of heat, means the heat formed in this above case should be used for gold. So same heat when you supply to gold, how much mass of gold, calculate the mass of gold with specific heat 0.13, that can be heated to the same temperature difference. So how much mass of gold we can heat by the same temperature difference, and also with the same amount of heat. So as they are given same amount of heat, so heat is equal to 2137.5 in second case into is equal to mass of gold, which you are going to find, because they are asking us to calculate the mass of gold, into specific heat of gold is given 0.13, so 0.13 into temperature difference is also same, that is 475. So by this we can find mass of gold M is equal to 2137.5 divided by 0.13 into 475, which is coming around 34.61 grams after calculation. So I hope it is clear. So these type of questions are easy and very important for entrance exam. Next. So before going to this, let us do some numericals based on, no, after completing of this topic we'll discuss. So calorimetry. What is calorimetry? So calorimetry is an experimental method of measuring heat changes in a chemical or physical process. As I told you, to study the heat of reaction, we will use the calorimeter. That is also called as calorimetry. So the device is calorimeter and the study is called calorimetry. Calorimetry is an experimental method of measuring heat changes in a chemical or physical process. It consisting of an insulated vessel in which a reaction can be carried out. A reaction can be carried out by measuring the change in temperature of the reaction mixture, calorimeter, and using the values of heat capacities, the heat observed or liberated, we can calculate during a reaction can be calculated. So the measurements can be at constant volume or at constant pressure. So this is the use of calorimeter. Again, I'm telling you what is calorimeter. By measuring the change in temperature of the reaction mixture, calorimeter, and using the values of heat capacities and heat observed or liberated during a chemical reaction can be calculated. So these measurements can be at constant volume or at constant pressure, very important. So the measurements can be at either at constant volume or at constant pressure, that is delta H. So constant volume is delta U, very, very important. The measurement can be done at constant volume. QV is also called as change in internal energy, and QP is also called as delta H, that is change in enthalpy, energy of the system, change in enthalpy, and this is change in internal energy. When you take volume into consideration, internal energy only. When you take pressure into consideration, external energy, that is delta H. Very, very important, these 2 points. Let us see what is calorimeter now. Delta U is measured in a bomb calorimeter. What is delta U? Change in internal energy or change in enthalpy? Change in enthalpy or change in internal energy. Change in enthalpy or change in internal energy of a system. It is connected directly to volume. If volume is 0, delta U is also 0. If delta V is 0, delta U is also 0. That's why I told you, if delta U is equal to, sorry, if delta V, that is change in volume of the system, is equal to 0, means delta U also automatically becomes 0. So it contains a steel vessel. So it is a constant volume calorimeter. It is also called as what? Constant volume calorimeter. It contains a steel vessel bomb in which the combustion of a substance is carried out in excess of oxygen. So whatever substance we are going to heat, that will be burnt. That will be burnt in the excess of oxygen. It is surrounded by an insulated vessel because to withstand the heat, we'll use insulated vessel containing water whose rise in temperature is noted. So if you take water in the container and taking thermometer, so by using this combustion reaction, we can easily measure the rise in temperature. Knowing the heat capacity of C, the calorimeter, delta U is calculated as follows. What is delta U calculation? Very important. Please note it down. Heat evolved by m grams of a substance. The heat evolved by some mass of a substance is equal to heat absorbed by calorimeter. This is called heat lost by hot body is called heat gained by cold body. Simple. Heat lost by hot body. Because the substance which we are going to burn, it is called hot body. Heat lost by hot body is equal to heat gained by cold body. That is called principle of method of mixes. Heat gained by cold body. This we are done in school level also. So in the 11th class, we'll change it. Heat evolved by m grams of substance is equal to heat absorbed by calorimeter, that is C delta T. So heat evolved by m grams of a substance, that is m is called molar mass, is equal to delta U is equal to C delta T, m into m, where m is its molar mass and delta T is its temperature, small m is the mass of the substance. So this is the formula we are using for finding delta U. I hope it is clear. So delta U is equal to C delta T into m by m. Bomb calorimeter. This is called bomb calorimeter. So here we will supply oxygen. Oxygen supply will be given. Method of mixer stirrer will be there. Insulating jacket, bucket, heater, water, ignition coil. Because by this heat is generated. Sample steel bomb. The steel bomb is nothing but what? the mixture which we are going to burn. And crucible is nothing but container, airspace, and here you'll keep thermometer, magnifying eyepiece. So by the change in temperature, we can notify the molar heat capacity. Already we know. So by the change in temperature, we can find delta U. Delta U means change in heat at constant volume. This is called bomb calorimeter. What is the use of stirrer? Stirrer is to mix the substance. Insulating jacket to protect heat. Bucket and all other things. So I hope it is clear. And this is heater for generating heat. Water is getting heated up because of the combustion of substance. That because heat lost by hot body is called heat gained by cold body. Water is a cold body. So when the water gains the energy, so heat energy, automatically the rise in temperature takes place in thermometer. So due to this, we can calculate what is steel bomb. Steel bomb is the mixture which we are going to burn. That is sample ignition coil because for getting heat. I hope it is clear. So this is the bomb calorimeter where we can find out the heat capacity of the mixture. Next, measurement of delta H. The reaction is carried out in an insulated vessel directly at constant pressure. That is delta V. This is delta U. That is delta U is nothing but what? I'll tell you the difference. Delta U will measure at constant specific heat capacity, constant volume. Now we are going to measure delta H. Delta H is nothing but the reaction is carried out in an insulated vessel directly at constant pressure calorimeter. The reaction is carried out in a polythene bottle and the rising temperature of the reaction mixture is noted. The temperature may rise or fall depending upon whether the reaction is exothermic or endothermic. So it may rise or fall depending upon the reaction, whether it is exothermic reaction or endothermic reaction. I hope it is clear. Next. Measurement of delta H. So the heat liberated or absorbed is calculated by using the formula Q is equal to delta H, where delta H is equal to ms delta T, mass of the substance into specific heat of the solution into delta T, that is rise or fall in temperature. Mass of the solution, specific heat, Q is heat liberated or absorbed. Here it is assumed that no heat is absorbed by the polythene bottle or by the insulated vessel. So this is called calorimeters reaction mixture. So it is burnt again. The rising temperature is noted by using thermometer. This is ice bath. So stirrer will be kept and the reaction mixture will be taken here and it is ignited. Ignited means it is burnt, combustion. So let us see now some more questions based on, now we are going to discuss questions based on today's concept. Very, very important. These questions, how we will get questions, only one question so far we have discussed. So now I'm taking questions based on today's concept. Let us see now. Yes, let's start now. Yes, taking white sheet. That's why I want to know the questions. So I'm discussing the questions right now. Let us see questions based on today's concept. Very, very important. These are all questions important for entrance exams. So questions based on measurement of delta H or delta U. So measurement of delta H and delta U. Delta U or delta U is same. So it's very, very important. Most important questions. Now question number one. The same question has come. So question number one now. The difference between heats of reaction at constant pressure, see here, as we are discussing, heats of reaction at constant pressure and at constant volume For the reaction, they have given burnt benzene with excess of oxygen. So 2 moles of C6H6 plus 15 by 2O2. This is gas, benzene is liquid, giving rise to 12 moles of carbon dioxide gas plus 6 moles of H2O gas, liquid. So at 25 degrees C, at 25 degrees C, in kilojoules per mole is option A minus 7.43, option B 3.72, option C minus 3.72, and option D is 7.43. Very, very important, this question. So how to calculate the difference between heats of reaction at constant pressure and at constant volume? For the reaction, 2 moles of benzene liquid, when burnt in excess of oxygen, it forms carbon dioxide gas and water liquid. So here liquid and liquid, these two be eradicated because it is applicable only for gases. So here if we take, already we know delta H, they are asking difference between heats of reaction at constant pressure. Heats of reaction at constant pressure is delta H of P minus delta U of V, because heats of reaction at constant pressure is delta H, and heats of reaction at constant volume is delta U, and this is equal to delta N RT for chemical process, delta N RT, where delta N is equal to, what is delta N value? Number of moles of gaseous products, only gaseous, very, very important, minus number of moles of gaseous reactant, This model is very, very important. Many times they ask in entrance exam, so that's why I'm doing. So delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants. So what is the product here? 12 moles. 12 minus 15 by 2, that is 7.5. 15 by 2 can be taken 7.5. So 12 minus 7.5, because 12 moles of carbon dioxide and 5 by 2, 15 by 2. Sorry, it is 15 by 2. No, it is 15 moles. Sorry. It is 15 because balancing will not be there. So 15 moles of oxygen and 12 moles of carbon dioxide. So 15 and 12. So 12 minus 15, it is 3. So delta N value is equal to how much? Since delta N is equal to, first we'll calculate delta N. Delta N is equal to 12 minus 15, because number of moles of gaseous products is 12 minus gaseous reactant is 15. So 12 minus 15 is equal to minus 3. So by this you can say delta H minus delta U, because they're asking this only. Delta H minus delta U is equal to minus 3 into R value is 8.314 into temperature value is how much? Temperature value is given 25 degrees C, means we have to convert into Kelvin, so it is 298. This the value will get in joules. So let us multiply this. Minus 3 into 8.314. 3 into 8.314 into 298 into 298 is equal to 7432. That is minus 7432 minus 7432 is equal to minus 7432.1. That is joules, but we have to convert this into kilojoules, so it is equal to minus 7.432. 7.43. So answer is first option, minus 7.43, because this is in kilojoules, because 7432 divided by 1000, so it is approximately 7.43. So 7.43 kilojoules. I hope it is clear. So this type of numericals. So the difference between heats of reaction at constant pressure and at constant volume. Heats of reaction at constant pressure is called delta H, and heats of reaction at constant volume is delta U. So delta H minus delta U is equal to delta nRT, and since delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants. So number of moles of gaseous products is, so it is 12 minus 15 is equal to 3. So delta H minus delta U is equal to minus 3 into 8.314 into 298. This answer you will get after multiplication, you will get in joules. So convert them into kilojoules because answer they are asking in kilojoules. So minus 7.43 kilojoules is the answer. So answer is first option. I hope it is clear. So this type of numericals are most important. So please note it down in your classwork. Next question number 2. So for the reaction, so this is in chemical process I'm doing. For the reaction, C2H4, that is ethene, plus 3O2 gives H2, because this is also an organic compound like benzene. So any organic compound when burns in air oxygen, it forms carbon dioxide and water. So straight away we can write 2H2O. So this is liquid, this is gas, this is also gas they have given, and carbon dioxide is anyway gas. Now what they are asking, the difference between enthalpy change and internal change is internal energy change. So the difference between, so they ask the same question in different pattern. The difference between enthalpy change and internal energy change. Same question they asked in different statement. Internal energy change is option 1 minus RT, option 2 plus RT, option C, this is previous NEET question, minus 2 RT. For NEET, we no need to calculate. For JEE means they give calculation patterns, plus 2 RT. So now here they ask, instead of asking the difference between heats of reaction at constant pressure is called what? Enthalpy change, and constant volume is internal energy change, as I already told you. So that's why this we can take it as delta H minus delta E is equal to delta H minus delta E. What is delta H or delta U? Sorry, either E or U is same. So just waiting. Delta E or delta U, both are same. Don't to get confusion. Is equal to delta N RT. Delta N RT. How to calculate delta N? Already we know in the previous question only we have seen, that is number of moles of gases products minus number of moles of gases reactants. So straight away if you find delta N value, you'll get the answer. So delta H is heat of reaction at constant pressure and delta U is heat of reaction at constant volume. So heat of reaction, instead of asking heat of reaction at constant pressure and heat of reaction at constant volume, they have asked difference between enthalpy change and internal energy change. Is difference between enthalpy change and internal energy change. They are asking enthalpy change and internal energy change. So instead of asking heat of reaction at constant pressure and heat of reaction at constant volume, they have asked like this. So both are same. That's why I want to tell you. So next, delta N is equal to, how to calculate delta N? We already know, number of moles of products minus number of moles of reactants. So it is nothing but, in products we have only carbon dioxide as gas, because for liquids no, what is it? For liquids it is taken as, it is liquid, it is not applicable, only we have to consider only gas. So number of moles of products minus number of moles of reactants. So 2 minus 3 plus 1, it is 4. So 2 minus 4, it is equal to minus 2. So answer is third option, because delta N is equal to delta H minus delta U is equal to delta N, that is minus 2 into RT. So minus 2 RT is the answer. So for NEET, they will not give calculation. For JEE means they will give calculation for this also, taking R value, temperature value, 25 degrees C. Since they are not given temperature and R value, so straight away we can take this. I hope it is clear. Next question, question number 3. So like this question is most important. Next question, question number 3. Now we are going to discuss for which of the following reactions, for which of the following reactions, for which of the following reactions, comma, delta H is equal to delta E plus 2RT. Delta H is equal to delta E plus 2RT. This is application problem. Same question. Delta E and delta U are same. As I told you, delta E is equal to delta U. Both are same. What is delta E or delta U? It is heats of reaction at constant volume. What is delta H? Heats of reaction at constant pressure. So delta H is equal to delta E plus 2RT for which of the following reaction? Let us take first example they have given. Option A, nitrogen plus 3 moles of hydrogen gas is equal to 2 moles of ammonia. All are gases here. So you can take nitrogen gas, hydrogen gas, ammonia gas. Second option, nitrogen gas plus oxygen gas N2 plus O2 gives us to 2NO, that is 2 moles of nitrogen oxide gas. Third option, NH4HS, ammonium hydrogen sulfide, NH4HS, ammonium hydrogen sulfide, it is solid plus, ammonium hydrogen sulfide on decomposition, directly solid changes to ammonia gas plus hydrogen sulfide gas. So NH3 gas plus hydrogen sulfide gas. Next, fourth option, straight away, PCl3 gas, phosphorus trichloride gas, so it is PCl5. Phosphorus pentafluoride gas changes to phosphorus trichloride gas plus chlorine gas. So these are the 4 options we have. So now delta H minus delta, by this you can say delta H minus delta E is equal to 2RT. Yes or no? Because if you bring delta E to this side, it becomes 2RT. So for which of the following gas delta N is equal to plus 2, that is the answer. Where delta N is equal to plus 2, that is the answer. So delta N should be plus 2. So first case delta N value we will find. Let us find first case delta N value, because delta H minus delta E is equal to 2RT is given, because so that in the place of delta U, delta N is equal to 2, because you know the equation delta H minus delta E is equal to delta N RT. Delta N RT. So if you find delta N place is 2. So straight away delta N is equal to plus 2. So in this case, first case, let us see delta N is equal to 2 minus 4, it is minus 2. So it is not the right answer. Second case, 2 minus 2, it is 0. Delta N is equal to 0, because second case it is 2 minus 2, it is 0. Third case, it is 2 minus 0. So delta N is equal to gases is 2. So 1 plus 1, 2, minus number of moles of reactants. In reactant, there is no gas, so it is 0. So it is plus 2. So straight away, you can say answer is third option. No need to see fourth option again. So I hope it is clear. So this is third option. For which of the following reactions delta H minus delta E is equal to delta H is equal to delta E plus 2RT. So they have sent delta H, delta E to that side. So we already know delta H minus delta E is equal to delta nRT. So delta H minus delta E is equal to 2RT. So delta N is equal to plus 2. So for any of the, how to find delta N, already we know that is number of moles of gases produced. Delta N is equal to NP minus NR. That is number of moles of gases produced minus number of moles of gases reactants. So for the first case, delta N is equal to minus 2. Second case, delta N is equal to 0. Third case, delta N is equal to 2, because we have got delta N is equal to, because this is solid. So no need to consider. So 2 minus 0, it is plus 2. So answer is third option. I hope it is clear. This type of questions are most important. Next question number 4. Next model in this concept. Next model is also very important. It's straight JEE means question. Delta H minus delta U So from this molar heat capacity, you'll get this type of questions only mainly. So delta H minus delta U for the formation of carbon monoxide, for the formation of carbon monoxide gas from its element, from its elements, from its element at 298 kelvins is at 2, as I told you, know this JEE mains question, they'll give calculation part. At 298 kelvins is option 1, that is minus 2477.5, minus 2477.57 joules per mole. Straight away they have given joules per mole. Option B, 2477.57 joules per mole, 2477.57 joules per mole. Option C, minus 1238.78 joules per mole. And option D, 1238.78. Just see how close they have given the options. So you can guess either C and D or A and B. But anyway, you have to do multiplication. Then only you'll get the answer. So for this, what is the formula? As I already told you, delta H minus delta U is equal to delta nRT. And here one more important thing, they have not given equation for the formation of CO. So straight away you can take C plus carbon solid plus half O2 oxygen gas gives rise to CO. So delta N is equal to how much now? 1 minus 0.5. 1 minus 0.5, because 1 by 2 can be taken as 0.5 because carbon monoxide is a gas. So it is equal to 0.5. So delta N value is 0.5. By this you can see 0.5 into R value 8.314, that is universal gas constant, and temperature value is given 298 kelvins. So 298 kelvins. So we are multiplying this, is equal to, so 0.5 into 8.314, 0.5 into 8.314 into 298 kelvins is equal to 1238. So it is plus 1238.78. 1238.78 joules per mole. So answer is fourth option. So this is the question in JEE mains. But you should know this equation also. By the end of +2 also easily can understand how carbon monoxide is formed from its element. From its element they have given. That's why carbon I have taken. So carbon does half O to gives rise to CO. Half means 0.5. So 1 minus 0.5, because carbon is solid, should not consider. So 1 minus 0.5 is equal to 0.5. Hence it is 0.5 into 8.314 into 298. So please note it down in your classwork. So this question is very, very important. I hope it is clear. Next question. Yes. Next question, previous NEET question. So this concept is very, very important. That's why I'm doing all the questions. Question number 5. The molar heat capacity of water. The molar heat capacity. See here, molar heat capacity of water is given. Molar heat capacity the molar heat capacity of water the molar heat capacity of water at constant pressure C, that is Cp is at constant pressure Cp is 75 joules per Kelvin per mole. 75 joules per Kelvin per mole is Cp of water. Next, when 1 kilojoule of heat, Q, this is value of Q, when 1 kilojoule of heat is supplied to 100 grams of water, 100 grams of water, which is free to expand. 100 grams of water, which is free to expand, which is free to expand. The increase in temperature of water is the increase in temperature of water is option 1 0.24 K, option 2 2.4 K, that is 2.4 kelvins, option C 1.3 kelvins, and option D directly we need to find delta T 0.13 kelvins. So this is a question now. They have given the molar heat capacity Cp. So already we know. So Q is equal to QP is equal to NCP delta T. They are asking us to find delta T only. QP is equal to NCP delta T, where N is called number of moles, because they have given molar heat capacity. If they have given specific heat capacity, straight away we can take mass. But they have given molar heat capacity, so we should find first N value. So N is equal to how much? N is equal to how much here? So QP is given 1 kilojoule of heat. So QP is called 1 kilojoule. So QP is equal to, here I'll write the equation. QP is equal to 1 kilojoule, and specific heat is equal to, specific heat capacity P is equal to 75 joules per Kelvin per mole. And in this only we need to find N. N is equal to given weight by molecular weight. Given weight is how much? 100 grams. And we know molecular weight. So since N is equal to, again I'll write because you confuse the formula. Since number of moles is not directly given, 100 grams of water is given. So given weight by molecular weight. So that is given weight is 100 grams of water by molecular weight of water is 18. So 100 by 18 is equal to, we can take straight away 100 divided by 18, which is equal to 5.5. So it is approximately 5.56. So straight away we can take 5.56. So now QP is equal to, so that is N is equal to, delta T, we have to find delta T. So delta T is equal to QP divided by N into Cp. So that is equal to, QP is taken as 1 kilojoule is taken as, because this is in joules, so we have to convert kilojoules into joules, 1000. So that is equal to 1000 divided by N moles, that is number of moles is 5.56 into 75. So if you do this, you'll get the answer. So 1000 divided by 75, 75.5 into 5.56 is equal to 419.78. So 1000 divided by 419.78, 419.78 is equal to 2.38. So answer is 2.4. So that is equal to, I will write here QP is equal to, so delta T is equal to, after multiplying this we got 1000 divided by 419.7, so which is equal to 2.4. Okay, this question is very, very important. I hope it is clear. So these type of questions are most important. Next question. So please copy it on this. In this, what is given? The molar heat capacity. Since they are given molar heat capacity of water at constant pressure, because if they are given constant volume, it is 0, because straight away there is no change in temperature, because for constant volume work done is equal to 0, automatically temperature also that is 0. So that's why, so del N is equal to W by M, so we have to do like this. So QP is equal to, what is the formula? QP is equal to N into Cp delta T. If they are given specific heat capacity, we have to take M, but they have given molar heat capacity, so we have to take N. That is the difference here. So N means weight by molecular weight, that is 1000 by 18, that is 5.56. So delta T is equal to QP by N into Cp, that is 1000 by 5.56 into 75. That is delta T is equal to 1000 by 419 point something. So approximately you'll get 2.38, that is approximately equal to 2.4 kelvins. So it is very important model. I hope it is clear. Please note down in your classrooms because afterwards you will not see the slides here. So this is question number 5. Next, question number 6. Question number 6. 1 mole of an ideal gas. This is very important. This is a neat question. 1 mole of an ideal gas. This concept based question, please note it down. 1 mole of an ideal gas expands freely at 300 kelvins, 310 kelvins, expands freely at 310 kelvins from 5 liter volume to 10 liter volume, from 5 liters to 10 liters. The delta E and delta H of the process are respectively. The delta E and delta H process. Delta E value and delta H of the process are respectively. Since they have given 1 mole of an ideal gas expands freely at 310 kelvins from 5 liters to 10 liters. From 5 liters to 10 liters. So value of delta E and delta H. So they are asking us to find the value of delta E, that is volume is given from 5 liters to 10 liters. So first option A, it is 0 and 5 calories. Option B, it is 0 and 5 into 300 calories. 0 and 5 into 300 calories. Option C, it is 0 and 0. And option D, it is 5 and 0 calories. Very important. Please think it. Now, let us see the solution now. I'll do it on the board. Please note it down. So for free expansion, since it is given free expansion, expands freely. So free expansion, work done is always 0 because already we know in free expansion work done is equal to 0. Since work done is equal to 0, temperature is constant. Temperature is constant because they are given only at 310 kelvins. So delta U is also becomes 0 because it's an isothermal process. Since delta U is equal to 0, so delta H minus delta H is also equal to 0. Why? Because delta H is equal to delta U plus delta nRT. Since delta N is equal to 0, T is equal to 0, we can say delta U is equal to 0 plus 0. So delta H is also equal to 0. So delta U is 0 because work done is equal to 0. I hope it is clear. So answer is third option. Very important. For free expansion, W is equal to 0, T is constant, so delta U is equal to 0. So delta H is equal to 0. Why? Because delta H is equal to delta U plus delta nRT. So delta N U value already we got 0. Delta N no need to write because just water only will take later on, but temperature difference. There is no difference in temperature because it's constant. So since T is constant, so delta N into RT becomes 0. So 0 plus 0 is equal to 0. I hope it is clear. Very important question. So with this, I'm ending this class with the last question. That is question number 7. Last question, we'll do it now. Question number 7. Let's write a question. CV values for, that is specific heat capacity at constant volume. So molar heat capacity, this is CV is called what? Molar heat capacities. V is called constant volume. So the molar heat capacity at constant volume values for, this is very important question. Values for monoatomic gases. Please note down in your class of these questions. Monoatomic and diatomic gases are respectively. Option A, It is 1 by 2r, comma 3 by 2r. Option B, it is 3 by 2r, comma 5 by 2r. Option C, it is 5 by 2r, comma 7 by 2r. And option D, it is 3 by 2r, comma 3 by 2r. So this is the answer for monoatomic gases and diatomic gases. Very, very important this question. So please note it down. I hope it is clear. So this, I'm ending this class session today. So please go through the slides and please note down in your classwork whatever the questions given in the slides. First you note down the question and options, then straight away you try to work out after listening the key. I hope it is clear. Thank you.